All right, there are many learning objectives associated with current electricity. There's like 10 of them. Here they are. Show an understanding of the nature of electric current. And that's just kind of very general, right? So it's like, okay, as a student, I need to show an understanding of the nature of electric current. So you kind of need to have a definition, I would say. And then you build the understanding kind of from that. Like when I say electric current, what do I mean? Moving charges. Like if you just say, okay, charges like protons, those are atoms made of these things. If they're moving, that's a current. A moving charge is a current. It's a very, very straightforward idea. The charge is moving, it's a current. Think about like the water flow. In fact, it's a very powerful analogy to think about like water flowing in a river or a stream and electrons flowing in a wire. Okay, and if we can kind of revisit that metaphor there, that analogy, to help us understand like resistors, like throw a bunch of rocks in a water, we resist the flow of the water. We can put resistors in our circuit. That's kind of the point of a circuit, is to put resistors in it, because when we resist the flow of charge, then we convert their energy into other forms. We kind of talked about that with a filament, right? Like the filament resists the flow of charge and it gets hot and it glows. That's kind of what we want it to do. We're trying to get the incandescent light from. All right. Define charge in a coulomb. Solve problems using the equation Q equals IT. Derive I equals NAV. Solve problems involving the mean drift velocity of charge carriers. Define potential difference, EMF, and the volt. Use energy considerations to distinguish between PV and EMF. Define resistance in the ohm. Solve problems using V equals IR. Solve problems concerning energy and power and electric circuits. Go on to another page, does it? That's a lot there. Okay. So this will certainly take us, this week and probably the next. The next several chapters are all about electricity, and kind of really focusing on electrical energy, not so much magnetism, although we'll touch on magnetism. Electricity and magnetism, we want to think as students of physics as two sides of the same coin. Okay. And light is an electromagnetic phenomenon. Kind of know that going into it, that wasn't known to the scientists that were studying this stuff until James Clerk Maxwell sort of serendipitously did a calculation where he said, oh wow, these electric waves are the same as the speed of light. Like the speed of these electric waves that's just sort of theorized here, is the speed of light. And so kind of realized that light must be an electromagnetic phenomenon. Pretty cool. Okay. All right. So you've got a wire, like imagine this is a copper wire, and you've got charges Q, they flow through it, and that's what current is. Electric current is the rate of flow of electric charge past the point. Current is the rate at which charge passes by a point in the circuit. I like to think about it as like you're counting charges as they pass by, right? Like a lifeguard on the electrical sort of river there, lazy river, counting charges as they pass by. That's what the current is. How many charges per time? Does anybody know we measure current in? What unit? Or somebody say amps. There's a clue on the chalkboard today where it says the intensity of the electric current I equals Q over T. Current is the rate of flow of charge. And then it says charge Q equals RT. That's just sort of reorganizing that, right? To make charge the subject. So 1 coulomb is the charge that flows past a point in 1 second when the current is 1 amp. So, did you have a question? Coulomb is the unit of charge. So 1 coulomb is the charge that flows past a point in 1 second. That's the unit of time when the current is 1 amp, right? So amp is the unit of current. So when the current is 1 amp, that current flows past the point for 1 second. How much charge has flowed past? 1 coulomb. And remember that 1 coulomb is like 9 quintillion electrons. I think we calculated last week how many electrons does it take to add up to 1 coulomb of charge. That's a whole bunch. Because remember, each electron is like 10 to the negative 19. So it takes like that many to add up to 1. It's like 9.25 by 10 to the negative 8, or 10 to the positive 18, something like that. 9,250 quadrillion electrons. That's what we're talking about, current. And now you have like current that flows through like the circuits that are powering these lights, right? Or like your electricity or in your house. So what's a typical current? You know, like 5 amps, 10 amps. You know, those are pretty high currents actually. Okay, so like that would be like the current that would run like in a wire, you know, powering electrical appliances. You could look at like your, oh, in fact, volts, 2.0, that's the output. Current that's coming out of the wall. The primary device when charging it up. You know, chargers or devices, right? Because they're all currents and things like that. So a wall has a voltage here in America of like 120 volts. The little lab volt stations that you could, well, I guess you all can't see them, but sometimes when you plug your phones in, you plug their phone like the wrong receptacle. You got to the lab here. Learning electric. You don't want to like hear 120 volts that comes out of the wall because it's high voltage. Low voltage power supplies. Always different aspects of them. Okay. So when that light's on, you know, this is fine. You could plug your phone and charge, but we can adjust here kind of voltage coming out of these. Those are from 0 to 12. And it's a low voltage power supply. When you're studying, you want to kind of study with the low voltage power for washing machines. Like that. Okay, so we'll use those. And in fact, we need to be sure to use them. Because that way we can say, you know, Dr. Slade, I think you should science over here in this classroom. We'll say, what about my low voltage power supplies? The hardwired in the lab stations. I use them all the time. Ask the student. And you'll say, oh yeah, we use them all the time, every day. Low voltage power supplies. No, that's on footage saying all that. I'll edit it out. No, we really do. Okay. Define charge in the coulomb. So charge as current times time. So coulomb is the charge which flows past the point. Seconds and current is 1 amp. That's all written on the board over there. And elementary charge we talked about last week has that value. Thanks to Millikan, his famous oil drop experiment. And again, these slides are sort of up on focus for you to peruse at your leisure, and there'll also be a corresponding YouTube video that is being recorded right now. All right, solve problems using the equation Q equals IT. And it looks like, you know, we'll queue up some work example problems and questions, so we'll kind of take a look at that. But just like we always like to do with physics, like some unknowns, we got an equation that sort of relates what we want to know to what we don't know. I'm sorry, what we want to know to what we do know. What we want to know is what we don't know, and then we can solve for what we don't know. Here's another equation. It was the learning objective, derive I equals NABE. I don't know if this slide is the best sort of explanation of it. I think actually what I'd like prefer to do is I'm going to do this on a separate, if I can do one of those. if I go here, maybe this here button. All right, let's consider a giant block of metal. All right, and so this is a box of metal that is 1 meter by 1 meter by 1 meter. It's a cube. Think about how big of a cube this would be. Observe it here in the laboratory. Imagine building a box out of meter sticks, how big a box it would be. Okay, but now it's a cube of solid metal. All right. What metal is it? I don't know. Let's make it copper. Copper. So we've got this giant cube of copper metal, and we want to sort of exploit one of its properties, the fact that it is ductile, can be drawn into wires. So we're going to make some copper wire. Now, there's one thing that we could look up, or we could research about different metals, okay? And it is called their number density. Number density. Number density of a metal tells us how many free electrons. It's how many, I'm literally writing this in a Word document. Number density, how many, we're going to say free or conduction electron. 1 cubic meter possessed. Oh boy. The number density M is how many free or conduction electrons a cubic meter of a metal possesses. Okay, so it's like how many, now what is a conduction electron or a free electron? So we're typically talking about metals here. Metals bond in such a way that they pool their electrons together. So it's like electron pooling or metallic bonding. It's different than the way, like, I don't know, like in an acid, like hydrochloric acid, we got HCl. And the chlorine is very electronegative, and it basically steals away the hydrogen from the molecule. So it's a very polar molecule. So metals will tend to sort of share their electrons such that there's some electrons that are tightly bound to the nucleus, and so copper has, you know, what, 29 electrons. Every nucleus, okay, every atom of copper has 29 electrons, and probably one of them is a conduction electron per atom. So like one of those 29 electrons isn't very tightly bound to its nucleus, but could rather, it's free to like flow between all the neighboring, you know, copper atoms. And that's what really characterizes metals as being good conductors, is sort of how they sort of share their electrons, how tightly sort of the electrons are held in each atom. And so number density is just a way to quantify that, just a way to sort of do experiments to say, hey, copper has this number density, this many conduction electrons per cubic meter. A cubic meter is a huge amount of substance, right? It's a volume. You can imagine if we knew like the density of copper, we could calculate the mass of that. That would be like, you know, a lot. Okay, so we just define it because it's 1 cubic meter. It's like the unit dimension You got to guess like, well, how much are we dealing with here? Well, just choose a certain volume. It's metric system, so just a cubic meter. Okay. So how many electrons per cubic meter? That's what number density is. Can somebody that's very resourceful look up right now, what is the number density of copper? Like ask your artificial intelligence. You have access to know that. 8.96 grams per centimeter cubed. Number density. I think that's just the density of copper. I want the number density. So let's, not the density, the number density. And you might have to ask it this way, the number density of conduction electrons. Because this is mass, right? This is mass per volume. So this is the actual density, like how many grams of mass per cubic centimeter of volume. Anybody have that number density? That's right. Hey. Good morning. You know the number density of copper? Good morning. You know the number density of copper? You know the number density of copper? Yes, thank you for that, but I didn't know the number density of copper. Is it 1.7 by 10? I don't know about those letters. Yeah. The S and the. All right. What is the number density of copper? The number of conduction electrons of copper. Or this. 8.45 by 10 to the 28. Right. 8.45 by 10 electrons per cubic. I'm trying to verify that. That sounds about right. 8.45 by 10 to the 28. They're just electrons per cubic meter. So for copper here, the number density of copper is 8.45 by 10 to the 28 electrons per cubic meter. Okay, so the units are just like, it's a number of things, right? So that's why it's a number density, the number of electrons in this case, in every cubic meter of copper. That's a lot of electrons. There's more electrons in that cubic meter of copper than this. These are just the free ones. These are the ones that can actually go and readily conduct. You don't have to add energy into a conductor to get it to conduct, like you do semiconductors or non-conductors. Remember, like we couldn't get electricity to conduct through air, but we put a tremendous amount of energy into, sort of an electric field, and then we can get it to conduct. So you can force things that are for conductors to conduct by adding energy into them. But you don't need to do that. That's sort of what characterizes a metal. We say that their electrons are already in the conduction band. You can promote things that are in, a non-conduction band or a valence band for semiconductors by adding energy to them. We'll see, examples of that as we continue to study electricity. I think that's going to take off on my writing if I do this. Maybe not. Go down just a bit. All right, so we've got copper that's got a certain amount of electrons that are able to conduct. And remember, that's about 1 per atom. So there's, huge number of atoms in there, and each atom is basically contributing one of these conduction electrons to this. So now let's think about getting an equation for current. All right, it's kind of based on this. Like we're gonna take a piece of this copper, we're gonna draw it into a wire, and we're gonna send some current through it. So how can we get an equation for that? All right, let's sort of keep this in mind here. All right, so we take a piece of the block of copper and we start to draw it into a wire here. All right. And the wire is going to be cylindrical. Okay. You can think about the wire as being like, a cylinder. As a circular cross section. Let's start with the general equation for current. Current is the charge over the time. Okay. So we just like we got this equation for pressure, rho g. Remember how we got that? We started with the general equation for pressure, force per area, and we said, oh, density is mass per volume, and then we kind of combined these ideas. We said, oh, well, the force would be the weight is mg, and then we sort of substitute everything in, and we kind of get to this, right? You start with the general sort of definition. In general, pressure is force per area, specifically to hydrostatic pressure, things with a given density rho, there's a certain height of those, atoms with that density, sort of above a point, and that's what gives pressure. So we're going to do the same thing. In general, current is this. Let's get another equation for current sort of based on that. What are the charges? Okay, well, we've got the number density. That's where the charges come from. It's like, how many conduction electrons do I have? So I got the number density that's sort of creating these charges. But this is the number per what volume? An entire cubic meter, right? We sort of define it that way. We don't say like, hey, how many conduction electrons in this chunk of copper that I just mined out of the ground? Like, I don't know, but I know if you had a cubic meter of it, it'd be 8.45 by 10 to the 28. Because we define it like by a unit, like 8.45 by 10 to the 28. Remember, that's the number density of copper. So that's per meter cubed, right? That's electrons per meter cubed. So if we've got the number in a cubic meter, do I have a cubic meter of sort of wire here? If I had an incredibly long circuit, maybe. So we need is a way to like cancel out this volume. Okay, what is volume? Volume is the two-dimensional area, the area of the two-dimensional base, if you will. Like this thing would sit on a circular base if I set it on its sort of end here, times the third dimension. I'm going to call the third dimension for this one a length because it's a wire, right? So I'm drawing my copper wire into a length. Think about volume like this. Okay, it's actually the same way we derived this equation over here, but we just said it was like area times height. All right, so whatever you're calling the third dimension, the height, the thickness, the length, the depth, there's a 2D area, in this case a circle, times the length. What is the volume of a cylinder? It's pi r squared h. Because a cylinder sits on a circular base, pi r squared times the height, right? And this is the same thing. I'm just calling the height L because it's, I put it on its side. Does that make sense to everybody? Like if you were to look up in a map, but what's the volume of a cylinder? You find this formula. And now you can kind of appreciate it as, oh, I've got a circle with area pi r squared. I've got another circle area pi r squared and another one here and another one here. If I stack up these circles, h, I've got their volume, right? By multiplying their height h by the area. That's all the volume is, right? It's the 2D area times the third dimension. So I'm going to multiply my number density by that, by the volume. Now I cancel out volume. Okay, if I sort of think about the units down here, I have electrons per meter cubed. Now the area would be the area of this circle here, this pi r squared, and its units would be meters squared. The length is linear, right? So it would be meters. And so you see what I've done there with the units? I've got the number of electrons now. By multiplying the number density by the volume, you get the the actual number of electrons in your wire. My wire has actual volume A times L. It's going to depend on how long I make it, you know, what actual area it is, like how, you know, some wire out, it gets smaller and smaller, right, as you continue to sort of grow into a lengthier and lengthier wire. So it's like, this is the number in a cubic meter times whatever volume that I've got now in my sample, in my circuit. Okay, so this is the actual number you've got, not the number in a huge brick of copper, right? But the actual number that you got in your sample. In your wire, let's see, it's this one here that has area A, cross-sectional area A, and is length L. Like this term right here is the number of electrons in that, right? It may be that the area is a cubic meter, right? Maybe I drew this out in a big long wire, and so it'll just sort of be, okay, number density per cubic meter times the cubic meter, and I'll have this number. But usually it's going to be less, right? Like I'm not going to have an entire cubic meter wire, but something significantly less than that. So when you multiply it by the volume you have, you're like accounting for the fact that you probably don't have an entire cubic meter of copper, but we know if we did have a cubic meter, that's the number density. The way to just multiply to get the electrons you've got. What's the charge of an electron? Because here we just have a number of electrons. NaL gives us the number of electrons. I'm going to say that. NaL gives us the number of electrons in our wire. Right? That's the number density times the volume, NaL. But that's not a charge. What's the charge of an electron? Here we just have the number of electrons, 15. Okay, what's the charge on each one of those 15? Say it again. It is negative, but negative what? Say it again. Yeah, because each one is -1. I'm trying to ask my question in a better way. You're right what you're saying. So no, you're wrong. You're not. But you're wrong. You're not thinking what I'm thinking. Like, well, you're not asking. You're getting a question now. Electron has a charge of -1. Okay, but in terms of the base, in terms of the units, the SI units, what's the charge on an electron? Does anybody know the charge on an electron? (1.6 by 10 to the -19). But see how we're doing math with letters? So I don't want to start writing numbers down, 1.6 by 10 to the -19. Does anybody know a letter that stands for that? What letter do we use to stand for that? Little e for, and does anybody know why? Not for electron, but for elementary charge. So see if I multiply the number of electrons I've got in my wire by E, now I'll have the actual charge Q. We've got our numerator. I'll edit some applause in there, don't worry. All right. Divided by T. Kind of underwhelming there for the denominator. Note where I put that T. I didn't put it underneath the N or the A or the E. I put it underneath this L. Doesn't really matter. Other than that, I want to illustrate and emphasize a point here. What's L over T? Distance, L, right? L is a distance. Like if I had an electron here and it moved from here to here, it went a distance L in time T. What is that L over T? What is it? Speed, velocity, right? The rate of change of displacement. And so I can substitute in L over T, the velocity. And we call this V the mean drift velocity. Okay, so V is the mean drift velocity. And so mean, it's an average. Drift, because it's like when we put a battery up on some wires and build a circuit, the movement of the charge carriers through that wire is pretty haphazard and erratic, but there tends to be a drift in one direction. okay? But like the collisions between individual electrons are very fast, but they're not all going in the exact direction of like, you know, let's say right around the circuit or left, you know, sort of around the circuit. They're like crashing into electrons every which way. And if you average their motion, yeah, they tend to sort of drift in the direction of the sort of flow of current there. But the drift velocity is very, very slow, actually. So the individual collisions between electrons are very fast and have a lot of momentum, you know, so sort of transfer. But the net sort of movement inside of a current carrying wire is such that there's a slow in terms of the flow of charge. It's actually like millimeters per second. It's pretty slow. And we'll see sort of calculations of that. And so you'll see forms of an equation, I equals nave NAVE, and it's the number density times the area times the velocity times elementary charge. And sometimes B will be the subject of that. In other words, we'll be saying, well, what is the mean drift velocity of the electrons in a circuit whose current is, right? You'll have to know everything else about it. They're never going to be friendly enough to give you E. They're going to say, remember, elementary charge is this, right? That's something you're expected to know. Area can be difficult because they may give you the diameter of the wire. They might say, you know, here's a wire whose diameter is this. And you'll have to say, okay, well, if the diameter is that, then the radius is half of that. And the area would be a pi r squared cross-sectional circle, right? The cross-section of a cylinder would be a circle. And so you'll have to calculate the area A, pi r squared, from a diameter. Okay, not too bad, but an extra step or two. You know, you got to half the diameter, make it the radius, then square that, multiply by pi, right? Remember all this. The number density will be something given. Okay, will have to be given to you. It's copper, which has a number density of this. And again, those are just known values based on the properties of that metal. Certain metals are great conductors. They've got a lot of conduction electrons that are free, ready to conduct. Other ones, not so many. But all metals have, you know, conduction electrons. That's what sort of characterizes them as good conductors. So this is what this is all trying to say, I imagine. You know, it's all the same stuff. All right, and we'll see some, like I said, some more examples of that, solving for the velocity V. Not to be confused with the voltage. All right, and we want to define some things like that. Potential difference, EMF, and the volt. So when you think about potential difference in EMF, PD, EMF, they're both voltages, okay, measured in volts. I was like, well, why do we need two terms if they're just voltages? Can we just call it voltage? Why do we have one that's potential difference and one's EMF? And remember that there is another learning objective, probably on the next slide, yep, use energy considerations to distinguish between them. So they are the same thing in terms of the units that they're measured in volts, just like work and energy, both measured in joules. We got PD and EMF, both measured in volts. You know, why do we need two different terms for them? Because there's an energy consideration that we'll keep in mind and distinguish between them. While these notes up here are good notes, I really don't like slides like this in terms of a presentation. If you're presenting information, okay, like if I'm your physics teacher and I'm presenting you with information about potential difference EMF and the volt, these slides are just designed for you to access at your leisure so that you have the good textbook definition, right? But it's like, it's a terrible way to present to say, here's some text-heavy slides for us to read through together now, verbatim. All right, it's like, hey, read that, you know, on your own time. I'll kind of explain sort of what these mean. The point of these slides is that there is a, you know, repository of text for you to have the textbook definition so that you can transcribe them into your journal so that you can then, you know, sort of learn them that way. But usually, like, it, you know, so in other words, when I wrote these slides, I said, okay, we need slides just to have the definition. But it's not a good way to present, you know, it's just sort of a bunch of text on it. Better to have pictures, which is why if you look at most of my slides, there tends to be sort of images. You know, we can't really use text to get the definition So potential difference is we're taking energy out of the circuit. And we're not going to say, we're never going to use create and destroy, right? When we're talking about energy considerations, let's be very careful in our language. Let's say like gained and lost, or like transformed is even better. But if we can say, okay, the energy is gained here, it's lost here, what we really mean is like it's transformed from some other form into electrical energy. Now it's transformed from that electrical energy into some other form. The energy is gained or lost. You should sort of you shouldn't feel right or feel like, oh, here's what energy is destroyed in this component. No, we're not destroying energy. We're not creating it. Is this the thing that creates the energy in our circuit? No, we're never creating energy in this universe, right? It's a finite amount. Energy is neither created nor destroyed. We can't transform it. And that's really the point of circuits. It's our convenient way to transform energy, to enjoy all of the benefits of the technology. So potential difference is going to be the voltage like across a component. All right. There are devices, there are components, there are resistors, there are appliances, all those things interchangeably. So whichever one is familiar to you. An appliance, when I think of an appliance, I think of a refrigerator. Okay, that's like a component in your circuit. That's a device. And it really is just a resistor. It's a bunch of resistors. I mean, it's more complicated than that, but when we just sort of simplify it down to, we don't build circuits with no resistance in them. We don't just hook up a wire to a battery, because that's a short circuit. And when we study sort of one of the last learning objectives, Ohm's law, we'll see why we don't do that mathematically. That might be worthwhile to take a look at now. And again, all this stuff is here on Focus for you to access at your leisure and get all the best notes down. I'll explain through it. Okay, so this is called Ohm's law. Resistance equals V over I. And when you don't have resistance in a circuit, let's see here how we could sort of reorganize this. R equals V over I. So V equals IR is the way that I sort of suggest the student remember Ohm's law, because then you don't mix up the numerator and denominator. If you just remember V equals IR, then you can always, divide by what you need to make, R equals V over I or whatever. I equals V over R. Okay. So if we think about I equals V over R, the current I, started with that today, right? The intensity of the current. Here's another way to think about current. If you've got an equation in your notes from the central question, I equals Q over T, and now you've got another one, I equals NAVE, right? That's the current considering like the velocity and the area, like the actual wire. Now we've got one in terms of resistance and voltage. So I would equal V over R. Now, if I were to suggest to you all right now, hey, let's build a circuit with no resistance in it. Let's make the resistance 0. It's like, oh, I don't want to do math where I have to divide by 0. My calculator will break. So how could we maybe think about it? Let's say you can't really have a resistance of 0, because even the copper itself is going to have some resistance. It's going to resist the flow of charges some, but we can get it very, very close to 0. And so let's do a little bit of calculus here. Let's just make R like approaching 0. Are you okay with that? Like we do a limit? Like what would be the limit of this as it approaches 0? Okay. Because we don't want to make it 0, right? That's, again, put a 9-volt battery in your calculator there. Don't really put a 9-volt battery. Put the value 9 in your calculator. Okay. And now divide it by 0. Don't really do it. Your calculator will start, sparking and smoke will come out of it, and it will self-destruct. Calculators don't divide by 0. If you're brave enough, try it. Okay. I will on mine. Okay. It's an old calculator. In fact, I've got a video on my YouTube channel called Calculator Checks. Some of you might have checked it out when we did a calculator check a few weeks ago. My youngest son, suggested we do a calculator wreck video. We get old calculators and destroy them. My dad is hacking it in a matter of time. Okay. So be on the lookout for the calculator wreck. 9 divided by 0. Well, my calculator just says 0, actually. That's not right. 9 divided by 0. Okay, this one at least gives me an E. Oh, you all can't see. What does your calculator say when you divide by 0? Error. Divide by 0 error. I say explain it. Okay, so that's a problem. I guess this doesn't really explode or anything. That'd be cool though. You've attempted to divide by 0, your calculator will not self-destruct. So what we need to do is just make it like close to 0. Like make it, I don't know, that. That's pretty close to 0. Let's take our 9 volts and divide by, 0.0. As many zeros as you can fit and put a 1 at the end of it. So 9 divided by point. That. And what do you get? My calculator says that's 900 million or billion. You get the idea. Hopefully, even though we've only taken sort of one value, we could keep making this lower and lower. Use scientific notation. We could say, what's 9 volts divided by 1 by 10 to the negative 50th, or something like that. Like, let's make it really close to 0. 9 divided by 1 by 10 to the 9 divided by 1 by 10 to the negative 50th gives me 9 to the 50th, right? Because I'm dividing by it in the negative. So it's like that equals 9 to the 50th. So that would be the current. So when you build a low resistance or a no resistance circuit, that's a short circuit. What does it do? It tries to draw infinite current. In other words, the answer to this, like the calculus answer, the limit as this approaches 0 is infinity, right? It's just bigger and bigger and bigger and bigger. So eventually, it's approaching infinity. Can't get to infinity because that's not a number, it's like an idea, but we can entertain that idea of saying, oh yeah, these numbers keep getting bigger and bigger as I make this smaller and smaller. So that's why we don't build short circuits, okay? Because of this equation for current. Current is voltage over resistance, and if you build a circuit with no or low resistance, it will attempt to draw infinite current from the EMF source. Oh, I just heard another vocab. So the EMF is where we're putting voltage into the circuit. And that sort of connects it all back together. And we'll come back to Ohm's law here, but I wanted to give you yet another equation for current. So current is Q over G, current I is NAVE, and current I is V over R. And don't confuse that V, voltage, with the V in NAVE, which is velocity. Take care of the alphabet soup that is physics, okay? And it's like, no one wants to have to write out 0.0000, all the, scientific notation, 1.6 by 10 to the negative 19. Even that's, like physicists are too lazy to even use their own scientific notation. They're like, isn't there a letter we can just make like E? Oh, it's called E. I'm going to write out all these numbers here until I'm ready to do my final calculation. Like, so while you're doing the math, it's like, it's easier to calculate, it really is to write that symbol rather than writing 1.6 by 10 to the negative 19. And that's sort of, it's just a shorthand. But it can be very confusing. We know that it's like, I like my math with numbers. Let's get rid of this alphabet soup here. Plug in your numbers when you're ready to calculate the answer. Go back up here to the difference between PD and EMF. Okay. So the key sort of thing to hone in on here. I'm ready to pull back up. Charges lose energy by transferring electrical energy to other forms. Okay, that's PD. The PD, potential difference, we're transferring the electrical energy to other forms in a component, in a device, in an appliance, all right, is the energy transferred per unit charge. So voltage is always energy per charge, right? We talked about that on Friday. It comes to a question, how do I calculate the voltage, energy per charge, okay? And so I like to think about PD as like the minus energy per charge, okay? So like this is where we're losing the energy. We've energized charges as they go through a generator, through a battery, some source of EMF we say. Those charges get energized. As they go across some device, they power it, they lose energy. Where's that energy going? It's going into the light, the sound, the heat, whatever that device was doing. Okay, those charges get de-energized. And then they continue around the circuit to get re-energized again in the battery, and that will keep happening. Your light bulb keeps shining until the battery, runs out of energy. Right? The charges will no longer get energized, the light bulb goes out, the circuit stops working. Or we can decide to make the circuit stop working. A complete circle for the circuit to work, right? The charges have to be able to flow all the way around it. They got to be energized in the EMF, energized in some resistor. If you don't have a resistor, then you build a short circuit, and the circuit will attempt to draw as much current as it can from whatever source of EMF you've given it, and it will fry it and destroy it. Right? So short circuit, not a good thing. The potential difference between 2 points A and B is the energy per charge as charge moves from point A to point B. That's a good textbook definition for potential difference. Okay, and it's just like saying that that's where we lose the energy. A power supply or battery transfers energy to electrical energy in a circuit. The EMF of the supply is also defined as the energy transferred per charge. So kind of getting to the next learning objective, here's where we're losing, and then the key word here is gaining energy per charge, or we're transferring energy to electrical. So note that this one is from electrical to other forms. And that would be like a good note to maybe sort of spell out in the journal. So you want to have a compare and contrast. The easy way to compare them is to say they're both voltage, they're both energy per charge. Okay, so why do we have two different terms? Because one is the energy gained per unit charge. We're putting energy into our circuit. So we're converting the kinetic energy of a water turbine, the Hoover Dam, okay, into electrical energy. That's our source of EMF, a water turbine. But right now we've got a little water turbine panels here, motor. Okay. Energy of motion. Okay, so the kinetic energy of the water flowing out of a little turbine, hook it up to a generator, tell the light bulb to shine. That's sort of the idea now. All right, and so that is a source of EMF. Okay, we're putting energy like into the circuit, right? The light bulb there was the PD, right? It was taking that energy source out of the circuit. The EMF is total work done per unit charge when charge flows around a complete circuit. That's a good way to sort of define it in the textbook. It's powering the entire circuit. Okay, so the EMF is like the batteries, the generator, source of energy. That's where we sort of convert the other forms into electrical energy. The PD converts the electrical energy into the other forms, into devices. And that's just something to sort of practice the vocabulary, kind of work with different problems, we'll sort of get used to that. But think about like paper 2. State what is meant by PD and EMF, right? You just want to have sort of these definitions in mind. Flashcards, whatever strategies will help you there. This, I think, is really just a restatement of a lot of those bullet points, kind of the same information, just with this learning objective. Okay, you use energy considerations. The other energy consideration is this: when we convert other forms of energy into electrical energy, that's EMF. We used to think it was an electromotive force. It was a force that was moving electrons, but it's not a force, it's a voltage. It is an energy per charge. So we forget what it stands for, and we just call it EMF. Okay, so like, what does EMF stand for? Like, forget it. Don't worry about it. It's a legacy term. So it originally stood for EMF, but now it just is the thing that it means, regaining energy per charge in the circuit. We kind of forget where it comes from. Resistance in the ohm. Ohm is the unit of resistance. Resistance is voltage divided by current, right? So it's a ratio of the voltage of the current. It's measured in ohms, same thing as a volt per amp, right? Because like the equation here, volts measured in volts, current measured in amps. So a volt per amp is an ohm. This symbol here, capital omega, is the symbol for an ohm. And I always try to encourage students to take some time with their omegas. Don't just draw a sloppy looking omega down when you're doing your calculations. Try to take your time and let's see some clean looking omegas out there. Sometimes these omegas look like horseshoes, any kind of other. I've seen some bad omegas in my day. Big omegas is good class. I got high hopes for you. All right, here's a way that you could relate these variables to each other and to power. Energy and power in electric circuits. Okay, let's jump over here one more time. And I want to show you this one now. What is charge per time? Anybody know what is charge per time? Yeah, follow it up. The intensity of the current. Try to think about this as current. I know it's I wrote it as intensity of electric current. That's just because we use letter I for it. So it's like, well, where does the I come from? It's the intensity of the current. Okay, it's like current I. All right, so this is current. All right, what is energy per charge? This is the intensity of the current. What's energy per charge? Energy per charge is not force. Say it again. I can't hear you. The electric field is the force per charge, not the energy per charge. What's energy per charge? Voltage. Look at the essential question from Friday. It was how do I calculate the voltage, the inference energy per charge, right, of a generator. So that's voltage. What do I get if I multiply charge per time times energy per charge? Yeah. Charge. Okay, so the charge cancels, right? And you get what? So the product of current and voltage is energy per time. What is energy per time? Charge does cancel. If we multiply charge per time times energy per charge, the energy per time. Now what is that? What's energy per time? Yeah. Power. Power is current times voltage. Okay. So this is how we can calculate power with electricity. We've seen it before as this, in general, work over time or the rate at which one form of energy is converted to another. You could look up in any appliance, okay, and probably your microwave is what you're most familiar with because, your cooking time, you need to adjust based on the power. So when I put those vegetables in my microwave oven, it's based on a 1,200 watt microwave oven. But other cooking times, like a 900 watt oven, I need to cook it a little bit longer. So power equals current times voltage. Power is current times voltage. And again, we just kind of say we've already defined power as energy per time, and we've defined current as charge per time, and we defined voltage as energy per charge. The math just kind of works to get that, right? Energy per time is power. So E equals IV. The two, I would remember this one. This is one to commit to memory for sure. Another one is V equals IR. And again, this is one way to think about Ohm's law. The way that we sort of saw it was V equals, or R equals V over I, and then we rewrote it as I equals V over R, okay? But if you remember this one, then you can always sort of derive either of those, right? By just sort of dividing what you need to. If you try to commit this to memory, and then you're like, well, wait, which one was in the numerator? It matters, right? Like R is not I over V. That's incorrect and you'll get it wrong. But this one's like a V equals IR, everything is in the numerator. You know what I mean? And then you can sort of say, oh, if I want R to be the subject, I'll divide by I. If I want V to be the subject, it already is. If I want, whatever. So I would remember P equals IV and P equals IR. You can combine those two equations in all sorts of ways. And all of those ways, or many of them, are contained on this little wheel here, where it's like, if you want to know current in terms of V and R, it's this. But in terms of P and V, it's this. In terms of P and R, it's this. So it's like, this is like defining all of those things in terms of each other. And so the way to read this is like R equals V over I, or V squared over P, or P over I. It's like, if you want to have all of those equations in your notes, you could queue up this slide and copy that down. But if you just remember the two that I said, P equals IV, that one, and V equals IR, that one, that's enough to get the rest of it. Like you can always derive anything else that you sort of need to just from those. Oh, for example, I should have been so quick to jump off of this page here. When we have P equals IV and V equals IR, those two, P equals I squared R and P equals V squared over R. Those three for power, okay? And again, like, if you just know this one and this one, you can say, well, how did I get this I squared R? See what I did? I just substituted in IR for V, and then it gives me this I squared R. Likewise, if I substitute in, like V over R for I here, I get this one. But these will be the ways that you'll see power equations like this. Those other ones there, that's like the square root of resistance, like, forget about it. These three right here, okay? These are the ones that you want to have. Electrical engineers, will talk about I squared R loss or Joule heating, okay? Like we lose a lot of energy as heat when we send things with a lot of current. This is why we have high voltage power lines. Okay, we don't send electricity with high current, but rather high voltage because we lose more energy along the way if we send it with high current. So there, the better that we know this, the more we can sort of leverage our knowledge to decrease the energy losses, right? We want sort of the energy that we harness to be going towards useful things. Yeah. Yeah, so voltage is potential difference, but it's also EMF. So the V there is for voltage. And remember, both potential difference and EMF are types of voltage. So when you see V in an equation, think about it as voltage. Okay, think about, okay, that's voltage. And then the question, you have to read the question and say, is this the voltage that I put into the circuit? Is it talking about the EMF or is it talking about the device? And so, for example, the question may say, what is the power generated in the light bulb? And then you know, okay, I'm talking about potential difference here because the light bulb is a device. But if it says, what is the power generated in the generator, right? Then that's the EMF, right? That's me putting energy into the circuit. So it's like EMF is batteries, generators, water wheels, you know, like anytime like a hand crank generator, right? Like I could, like here I let the water do the work, but I have a hand crank generator back there where I could, like human beings, you know, use their kinetic energy and convert that into electricity. Feel free to steal this idea, you guys, because I've mentioned it in the past and I really think it's a good business model. It goes along with this idea of converting human kinetic energy into electrical energy. And there's, you know, various ways that we've done this before. There's things called piezoelectric cells, which are like in high traffic areas, let the ground kind of inflect a little bit. So just kind of like the ground is kind of, I don't know, has like little, I don't want to say bounce pads, but kind of little like clicky switches, okay? And when you step on them, those little clicky switches transfer a little bit of that energy into some place where it can be stored. So electric cells over, you know, Times Square in New York City. There's a tremendous amount of energy by people walking. We can kind of harness that energy. So that's smart. But here's my idea. Open up a gym, okay, and it's nothing but exercise bikes and treadmills. And what you do is you have all of the treadmills and the exercise bikes hooked up to generators so that the human beings that pay you a nominal fee to exercise in your facility, you sell that electrical energy back to the grid that they generate. You know what I'm saying? So it's like you have to charge people to come and work out in your power plant. And at the same time, you're it's like a human power plant. Okay, it's like come in and work out here in my gym, but really you're just like, you know, like FPL, like you're a power plant there. You don't realize that they're going to work out in your power plant. You charge them to come work out, but you also charge, you know, the grid to sell that electricity back to them. So money on both sides of it. All right, so feel free to steal that idea. All right, I came up with it, but if you want to take it and run with it, it's yours. All right, just kind of keep me in mind because you're laughing all the way to the bank there. So like, they pay me. Now eventually they might get wise to it and they're like, wait a minute, you're making a lot of money selling this electricity, you're paying us to come and work out. And maybe that's you'll have to change your business model. But anybody like what if in the future that was the thing? It's like human, like you know, instead of exercising, you might as well go work out in a power plant, you know, movement to convert to electricity. Like we'll pay you $10 an hour if you know ride this exercise bike, or maybe they pay you by like the kilowatt hour or something like that. You can really go for you know a short period of time. So you know, a lot of times it's tough. You know, I'm gonna go work out in the gym and make a little bit extra spending money for this weekend. Okay. So once again, feel free to think that's a good idea. Take it, run with it. Run with it. Okay. Solve problems concerning energy and power in electric circuits. All right. And so what we just talked about, power equals current times voltage, power is work over time. So we got a lot of equations today. We haven't really done enough to sort of think through the ideas, you know, with all of them, but that's kind of how it goes, right? So here we just write down the definition today, lay that foundation down so that as we continue to talk about it,